Good morning to everyone. And I'm told there are questions, but before we go to that, we'll go back to Rod Stewart, and it was Someone Like You, is that the title?
Actually, it was Reason to Believe.
Reason to Believe.
People are having trouble today, but there is a reason to believe, and you will clear it up today.
That's a good segue. Very good. Reason to believe in algebra.
In you.
Okay. Well, Jennifer, you have a question. Fire away.
I have problems with the whole section. But
So, not any particular, just the whole thing.
no, like there were 5 problems that I could not.
Okay. Which would we like to start on?
I guess 11.
11 for a start.
Yeah.
So at least we got past the first page of the homework.
Yeah.
We're on page 558, so this is a help. Now, why, when you look at 11, do you know you're in trouble right out of the gate? Let's see if I can get that. Okay, Debbie, let's try that. Focus is not the greatest. What's the problem with that immediately? On the left side, it said that you have a principal root, which is positive. But on the right side, you're supposed to have a negative 2. You know that can't be. So when you get done, the answer won't check. Is that what happened?
Yeah, I didn't think about that.
But you tried checking and it wouldn't work.
Yeah.
And it shouldn't. Because you had an impossible situation at the beginning.
So it was a no solution.
Right. Not fair, right? They're supposed to be answered. Okay. Now your second one. We took care of that one in a hurry. Your second one.
21.
21. Okay, just a moment. Let me try to get the little bit cleaner. Okay, 21. So on that one, we should have a solution. At least there's not a conflict at the beginning. So did you have k squared on the left side? When you squared both sides, then you had k squared minus 5k minus 15 on the right side. So what you end up with is minus 5 times k plus 3, so k is equal to minus 3, and that's a conflict. Doesn't check either.
Right.
Is that one that didn't work for you either?
Yeah.
Did you get k equals minus 3?
Yeah.
That's good. You did a good job. Okay, but again, it's one of those cases where the solution we think is a solution isn't. That's why we check them. Okay, so we got 2 out of 5. This is good. Going on.
Number 39.
39. Okay, 39. So we isolated, right? And had the square root of x equal to 2x minus 6. Okay, what happened to this one? I have no idea. I mean, I can factor out 2 and have x minus 3. So that's going to be x squared minus 6x plus 9, and I'm going to have 2 times that, and it looks like a mess. So it looks like we better talk about this one. We'll see what we can do. So let me write that one on the board. And that is the square root of x is equal to 2x minus 6, number 39. And page 500 what? 7? 58? Page 558. Now I simplified what was written in the problem because I've brought the 6 out of the left into the right. And I made the comment when I was talking about that is actually this, which might make it a little bit easier to do when I square both sides. I like factoring. It's your step, Jennifer, so you should really like that one. So as I square the left side, I'm going to have x. As I square the right side, I'm going to have a 4. I like that out front. And then I have a binomial squared. So that's going to give me x squared minus 6x plus 9, which is what I was talking about. Okay, so far? And I just think that's easier to square than 2x minus 6 is to square. But whatever the case, that's x, and that's 4x squared minus 24x plus 36. This is going to be an interesting factoring because I'm going to have a 0 there. And I'm going to have 4x squared minus 25x plus 36. We in agreement so far? And I've got to factor that. So what are my possibilities? 1, 4, 2, 2, and 4, 1 if I reverse one pairs of that. And then here I have 136, 218, 312, 4, 9, 6, 6. Have I got everything? And I want a positive, and out of that I want 25 as a positive, and I've reversed over here. And what I'm looking at now, this one won't do it. I'm coming across. This one will not do it. This one won't do it. This one won't do it. Okay? No. No. 6 and 24, no. Sheesh. And no there. 6, no. Okay, 4, 1, I'm getting a no, a no. That's where I'm going. I'm down now to the 12 and 12. And finally, I was working my way through. It's the next to the last one the way I set it up, which is frustrating. I should have started the other way. So the 4, 1, and 4, 9 give you a 16 and 9, which is 25. That was not one that I saw in my head immediately, and I had to break it down. But what I was doing was just taking everything with 1, 4, everything with 2, 2, everything with 4, 1, and was starting to get a little bit nervous when we got down to here and still didn't have anything working. So now I know I can factor that. 0, 2 binomials, and I need a 4, 1 and a 4, 9. So I need a 4x and an x, and I need the 4, 9. The 4 is out here, the 9 here. And both of them are negative, and that gives me 4x squared. It gives me a negative 25x and a positive 36. So that says 4x minus 9 is equal to 0, or x minus 4 is equal to 0. That says that x can be 9 over 4, and I'm just really excited about substituting that one in. Or x equals 4. Now, what am I obligated to do? Check the answers. And I think with what happened in those two first problems that we had, you understand why it's appropriate to do the check. So let's see what we have. The square root of 9 over 4, and I'm wanting to know, does that equal 2 times 9 over 4 minus 6? That's my question. Well, on the left side, I have 3 halves. Here, I have 9 halves minus 12 halves. Now, I changed the 6 to 12 over 2. 3 halves, negative 3 halves, does not equal. So, 9/4 is not a solution. 9 over 4 is not a solution. What about the 4? Well, the square root now of 4, and I'm asking, is that equal to 2 times 4 minus 6? Well, I get a 2 here, and an 8 minus 6, and that's 2. That checks. So I have one solution. Okay, Jennifer, does that answer? Out of curiosity, where was the question you had? At what point?
I was just lost in the beginning.
In the beginning?
I don't know what I was doing. I kept going around.
Does it make sense now?
Yeah, it does.
Now, you did not have to factor out the 2 first. I just like that a little bit better than leaving it as 2x minus 6. Your choice, though. Any other question on that one? That was a good problem. Good test question.
No, not a good test question.
Maybe not
Vote.
a good test question.
Can we vote?
No. Does not voting for problems on the test. Although that's an interesting thing. We can go through and select problems and say, okay, you have to vote for something, though.
Number 1.
The first one in each set, right? Other questions? Jennifer, you had 5. We got through 4 of them?
She has
I was
2 more.
trying to get. Okay,
Go ahead,
2 more. Okay, I was being optimistic. I was hoping I'd done 4, but only 3. Okay, the next 2.
41 and 43.
41's right up there, and that's the kind we did yesterday, and you had to isolate. Now let me slide down to 43, and let's see. 43 is sort of nicer because I don't have to isolate anything. So let's look at 43 for the moment. They're both done in a similar way. And if by doing 43 that answers the question, maybe we'll luck out and I won't have to do one more, but we will do it if necessary. I have the square root of x, and that's equal to the square root of x minus 5, and then I have a plus 1. So there's my problem. We're going to square both sides because we've already isolated one radical. But when you isolate one, you're going to end up with what? When you square another radical, which you'll isolate. So we're going to square both sides. So I'll square here and square here. The left side becomes x. That's good. What about the right side? Square the first. Double the product. Square the last. So x minus 5. Double the product. Plus 2 times 1 times this. So I still have a radical with x minus 5 in it. Then the square of the last. Is that step okay? Michelle?
That's where I totally got lost when I was doing my homework. I
But
was
you got
like,
here
oh.
okay. You got here okay?
I got, no, I didn't get to the 2 times the square root of the x minus 5. That's where I
Okay, the FOIL
was
process.
trying to solve it all.
Okay, but you sort of have to,
That's where I lost it.
this is a plus b quantity squared. Remember, that's a squared plus 2ab plus b squared. What happens when I subtract x from both sides?
Get 0?
I get 0 on the left side. That's good. Then I have minus 4 on the right side, so I'll add 4 to both sides. So I think I have 4 equals 2 the square root of x minus 5. Yeah? Ah, but then divide both sides by 2. Then square both sides. And you're done. Well, you have an answer. There's some question on the looks I'm getting from a couple of you there.
I have a different answer. Oh, I'm sorry. I'm looking at the wrong problem. You're right. I'm looking at 41, not 43.
Okay, that helps to be looking at 43.
Okay, 43. Got
Now
it.
I need to check it, right?
Yeah.
Now, I don't anticipate a difficulty here, only because I ended up with what? A positive here and a principal here. The potential had been, if this had been a negative, and this a positive, then I would have introduced an extraneous solution by squaring both sides. Perry?
I got to back up here for a moment.
Up how far?
The very top.
There.
When we say we're going to square the first, twice the product of
A and B.
and define A and B then. Is it x5 squared plus 1?
This is A, the radical
right.
of x minus 5. This is B.
So I guess what I'm asking is what happened to the 1?
1 squared was?
But that's the second, right? Then we're going to square the last.
That is squaring the last.
But then where does this, there's 2 times the sum of the A and B at?
No, it's not the sum. It's 2 times the product of AB.
There's no,
Okay, that's where I'm lost.
Okay, so I'm saying that if we have A
Right.
plus B,
So then it is just x minus 2 pi squared, right? Because it's the product of it?
you said a square, and that's what I got lost. I have, the product is 1 times this
Which is itself.
times 2.
Okay.
Hence, to the square root of x minus 5.
That's where I lost.
Okay?
Yeah.
Because what I'm doing is coming back to this form and saying, if I remember that when I square a binomial, I get that trinomial. That's what we call the trinomial perfect square. So your center term is twice the product of these 2 parts of the binomial. And that was, this is A, this is B, so I'm taking the product of those 2. And you don't see the 1 because 2 times 1 is 1, 2. 2 times 1 is 2, the square root of x minus 5.
that's where I got lost too. Yeah.
But does that help? Now, this step where I just divided by 2 to simplify it, again, not necessary, but life's better when you keep things reduced as small as possible. Now, we still need to check our answer. Any other questions on what we did there? Okay. So I'm going to take the square root of 9, and I'm going to ask, is that equal to what? The square root of 9 minus 5 plus 1. On the left side, I have a 3. On the right side, the 9 minus 5 gives me a 4. The square root of 4 is the 2. I have the 1, and it works. Okay? Any other discussion there? Okay, Jennifer, a question on 41. How is that different from this? Do you see something notably different in 41 that you, if you were to do 41 now, would you feel comfortable doing it? Okay. Anybody else in 41? Thank you, Debbie. What are you going to do in the first step? I mean, if I'm going to isolate one of those, which one am I going to isolate to make life good?
The second one. Because
Yeah, the second one, because I can add the square root of x minus 4, and then on the right side have 1 plus a radical. That's better than having a minus sign. Is there a need to do that one? Okay, are there any other questions? We took care of Jennifer's questions, I think. And I think she was speaking for many. The voice of one speaking for many. So we're okay there. Then would you be kind enough to fold the papers and pass them in? And just a reminder that we are covering fractional exponents this morning. And the idea is that we'll have a set of problems for that you'll do. And then tomorrow, once we've answered questions, we will do the review of Chapter 7. Then on Thursday, Chapter 8, and miscellaneous questions that you have related to either 7, 8, or 9. And then on Friday, for the group in here, a test. For those who are doing the video, and there's an equal, in fact, a larger group right now, doing the videos, and that test is going to be on Saturday, and that will be at the 10 o'clock hour in room 123, Founders Hall. So that's yet to come. And remember a blue book. This is a reminder for the test. This is our third exam, and it'll be covering chapters 7, 8, and 9. We're thinking in terms of 20 questions again, and so that's roughly 6 per chapter. And there's our 6 sections, roughly, per chapter. And so you can think something like each section is going to have a question on it. And with 20 questions, that seems to work about right for the hour. And I'll again be inclined to take sort of a medium level. It will not be the first problem in each section, in spite of the suggestion. But it will be something moderately there. However, a disclaimer there. The last problem, 43, happens to be at the end of a section. I like that kind of problem. So occasionally I will throw in one near the end of the sections because they are more interesting. Okay. We're going into fractional exponents. I know you can't wait. Okay, the definition. We've talked about this already. And the definition here is the important part, because if you understand what the radical means, then the other things are, as we go to this now, the other things we do with this section are just repeating your rules. But let's look at what we have here. A to the 1 over n means the nth root of a. It's that straightforward. Now, with that in mind, what are the rules we've had for exponents? Think of the things we've done. And we're going to sort of review those. It isn't quite set up this way in the book, but I'd like to go back and review those rules. And I have a little bit of room over here left in the front. So if we had an a and a b, and typically we've done m and n's as exponents, is that right? So we have a to the n, b to the n, those kinds of things. So that's what I'm going to look at. And I think I'm going to use at the far right there where I have that section that sort of goes to the top, and we'll go to there. So we've done things like this. If I have a to the m, and I multiply it by a to the n, what has our rule said with exponents? That is equal to what? A to the m plus n. Straightforward. And the quotient rule. If I have a to the m over b to the n, that is, I didn't do that well. I mixed rules in the process. I was wanting to get to AB's, and I'm not supposed to be there yet. So that is a to the n. Sorry. A to the m over a to the n is a to the m minus n. Right? And then we said if you had a to the m to the n, you have a to the m n. And trying to enunciate clearly the product of the exponents. Now, the question. Is there any restriction at this point on m and n? When we first set this up, we argued that m and n had to be what? Positive. And when we did things like this, we had a somewhat implicit restriction that m minus n had to come out of positive. So that forced us to then define a negative exponent. So we then, as part of this, said a to the minus m is 1 over a to the m. And now there was not a restriction that m or n had to just be positives. M and n could be negative. And the only place we had a restriction, m could not be, in general, well, not even there. I was going to say we have a restriction on 0. No, it just doesn't make sense. If you say a to the minus 0, it's still a to the 0, which is 1. But there were no real restrictions here. So if I had, for example, a fraction for m, like 1/2, and n was 1/3, it's still going to be true that it's going to be 1/2 plus 1/3. Okay? In that sense, all the rules work whether or not m and n are positive, negative, or fractions. The only restriction would be that if I had a to the m over n, let's talk about that one. How would we interpret a to the m over n? Well, we would there have to say that n could not be what? 0. But the question is, how do we interpret that particular statement? Well, that could be a to the 1 over n to the m, right? Or we could argue that is also a to the m to the what? 1 over n. Now that's a little bit of a wrinkle, but that's not much different than saying if I have a to the mn, that is the same as this, but it could also be what? I could have argued that that is the same as a to the n to the m. That still works. Nothing's new here other than the appearance of the exponent. What worked before will work now. Let me leave those up on the board just for a moment. Those are the things that we have to be able to do. So the last part of what I just talked about, and this again can be a little bit disconcerting, I'm going to go to the top of 563, and this is bouncing back and forth between fractional exponents and what? Radical signs. A to the m over n is a to the 1 over n to the m. That's what we just did in the board. But what I didn't do in the board is rewrite it as what? The nth root of a, all to the m power. In the same way, as we come off that, there's this statement, which is somewhat obvious in a way. If we allow for a negative exponent, then that's just by definition. If you have a to a negative exponent, it's 1 over a to the positive exponent. The fact that the exponent is a fraction, things still work as they did before. So I hope that doesn't particularly upset you. But the rules beyond that are pretty straightforward. It's just deciding what you're going to do with it. Now, I'm thinking here, I'm in trouble on the front board. So Debbie, let's try going to the sideboard, because there isn't really something that allows you to adequately, I think at least in terms of a statement, that allows you to see something like, do I want to do an odd number? Probably not. Let's try 46. Let's cut to 46. Now, the advantage of 46, it's with numbers, right, rather than letters, and I hope that helps you. So as I look at 46, I need to write it first before we cut to the board. That's 3 to the negative 3 over 4, and it is times, the dot is indicating the multiplication, 3 to the 5 over 4, and that's over what? 3 to the negative 1/4. Now, part of the problem here is to see something like this and not immediately get negative in attitude. I mean, you look at it and you say fractions, and then the next thought is, I don't like it, and to run away from it. If I had given you instead, and I'm going to contrast that, 3 to the negative 2 times 3 to the 4th over 3 to the negative 1, that would have been a problem that you would not run from, I hope. You would simply argue that in this problem I have, you would add the two exponents up here, so you'd have 3 to the minus 2 plus 4, and then you'd do what because you're dividing? Subtract the negative 1. That would be one approach. Or, we've done this before, where you say, I'm going to rewrite this. And so you did what with the 3 to the minus 2 the last time we saw these? You brought it down below, and the 3 to the negative 1 you brought to the top. And so you rewrote this as 3 to the 1st, 3 to the 4th, over 3 to the 2nd. And that meant you had 3 to the 1 plus 4 minus 2. Well, isn't that what you have here? Mm-hmm. That's going to be 3 what? To the 3rd power, agreed? So your answer, either way here, comes out 3 to the 3rd. Now, my point in looking at an easier problem, what I did here is what I should do up here in the same way. So what are your options? You could make this a positive exponent by bringing it into the denominator and the same with this 3 to the minus 1/4 and bring it to the top. Or you can do what? Simply argue, I have negative 3 over 4 plus 5 over 4 because I was doing what? I was multiplying. And then subtract off what? The exponent down here because I was dividing. So I'd have minus a minus 1/4. These are analogous. What is the alternative? To treat it just like I did down here. Now I'm hoping we can just come up here and say, well, that's 1/4 and 5/4, which is 6/4 minus 3/4. So you have 3/4. So this is going to be 3 to the 3/4, and I'm done. Now, if I take the option of taking the 3 to the negative 3/4 and rewriting it in a denominator as 3 to the positive 3/4, it's just going to avoid having what? Negative exponents in the problem. We did that before because we wanted to write your answer so it did not have a negative exponent. What did the rule or the problem ask me to do in this case for the answer? What does it say? Do I have the restriction of a positive exponent at the end?
Yes.
Let's write each answer in exponent.
Okay, so we're still making that as a restriction. So to that extent, you still might look at this as an option. Rewrite this without negative exponents right out of the gate. Is there any problem? I mean, we've talked about this before. I did it here. Let me, because this one has been rewritten. Is there any question of how I did this? With 3 to the minus 2, then went into the denominator as 3 to the second. The 3 to the negative 1 in the denominator became a 3 to the positive 1 in the numerator. It's like you have a ground level. This is the basement. This is the first floor. And as you go in between, the sign just changes depending on where you're going to write that factor. Are we okay? Okay, let's come back to the document cam. Now that is in some ways an easier problem than say 54, because what are you doing in 54? You're working with letters, and I think there's that general sense that letters are going to be a little more uncomfortable. But as we look at 54, what is your option? Well, since I have the 1/2 out here, that's like a square root. And what can we say about square roots? The square root of a quotient is the what? The quotient of the square roots. The square root of a quotient is the quotient of the square roots. It's just playing the game with words. So as I look at 54, the first thing I might do, I need to write the problem again, m to the 2/3 over n to the 3/4, and then I have that all to the 1/2. So what I'm saying, one approach is to immediately say, well, that's m to the 2/3 to the 1/2 over n to the 3/4 to the 1/2. But you don't have to. What can you argue immediately? You could argue just mentally that you're going to take 1/2 times this and 1/2 times the 3/4. But this is probably a good intermediate step to help clarify what's going on. So what is the argument? Now, if I take camera 1, Debbie, and I go to the a to the m to the n, that's that third one over there. We'll cut to that in a moment so people can see that on the video. It's the third one down from the top on the right side. A to the m to the n is just a to the m n. You're multiplying those exponents, and it doesn't matter if they're what? If they're fractions or not. So based on that rule that's very nicely in the middle of the screen, you would argue that I have m to the what? How about canceling the 2's and say 1/3?
Sorry.
That would be a little bit cleaner, I think, a little less of a problem. Now, what about the next in the denominator? Into the what? And here life isn't quite so good.
3/8.
3/8. And that's it. Yep, you're done with that one. Now, you could have gone from here down to here immediately in your head. I think for right now, it's a good intermediate step to sort of carry through so you remember what's happening. Now, again, the point being, we didn't really do anything different than we've done before. But because they're fractions, it seems different. Let's go back to the document, Cam. 54, 46, looking at 42. The thing that's going to be difficult about these, and in a sense, it's unfortunate that printing is still such that we feel obligated, as we look at this problem, 42, to write our fractions as what form? You remember what that's called when you put them on the same line? You have a 2/5 and you don't put 2/5, you put 2/5. You know the name for that fraction. It's called a Schilling fraction. And it was done 40 years ago because setting type and keeping it in the same line was an advantage. Now with the equation editors, it would be really neat to write that as a typical looking fraction, a numerator, a denominator. But what would you then need? More space in the book. And one of the problems that publishers have, if the book looks too thick, what is your conclusion?
It's hard.
Hard. So you write thin books to make sure everybody thinks it's not so hard. Small fonts, Schilling fractions, and make it more difficult to read the problem. Let's go back to 42 again. Now you understand that's 2/5 times 5/3, so what's the answer in your head?
2/3.
7 to the 2/3, right? Okay. Well, let's see if life gets any more interesting. Let's go to 52. Oh boy. Maybe I'll get to 52 if I can get the camera. Interesting thing, for those of you who are watching this on a video, one of the things I'm learning about this as we cut, and I'll shade it, if I get the camera lens too close to the book, it doesn't seem to be a problem in what I'm seeing or you're watching on television in the classroom. But if I get it down too close, the encoding magnifies the shadowing and really looks different than it was in class. So I'm having to learn how to use the camera in a slightly different way. There's 52. Now my point is, this is like a to the m, b to the n, all to some exponent. What other letter can I use? A to the m, b to the n, all to the s power. Something like that. So the question is, you look at that. What would you do as an intermediate step? That's my question. I want you just to look at the problem for a moment. Think intermediate step. Okay, let's come off there for a moment. And let's see if I can... There, I'll just slide it over, Debbie. And I can avoid glare. We can't read the fraction. It's right, the problem right next to it, but we can read the 52nd problem. I want an intermediate step. I think you can do that in your head as far as a solution, but I'm asking for an intermediate step. I'm trying to anticipate some problems that you may have this evening. We have p to the 4th, q to the, and I'm going to write it not as a Schilling fraction, but as a regular fraction, all to the 4/3. Let's come to the board now. I think this is an important intermediate step for you, to rewrite the problem with not Schilling fractions, so you clearly see something like this. Now, just a comment. 4 is the same as what? 4/1. So that's a fraction, if you will. So if you're going to multiply 4 times 4/3, you're going to get 16/3. I hope that's comfortable. But my intermediate step I was talking about. I think this is worth doing right now because there are so many places that you can lose it here. So if I write that as an intermediate step, the only danger here is canceling those 4s. So you might want to think of that as 4 over 1. Now, with that done, this is 16 over 3. And what happens to the 1/2 and the 4 here? The 2 and the 4 can cancel, so that's going to become q to the 2/3. Now, if you wrote 4 over 6, technically you have a correct answer, but what's understood? That you're going to, what? Have your fractional exponent reduced. So that's the argument. Any question in that one? Now, how would these problems differ if you kicked it up one level into intermediate level algebra? You'd have like p to the 2/3, q to the 3/4 over r to the minus 3/8, all to the negative 1/7. You just make them look a little bit worse or more entertaining, depending on how you perceive that. Now, I'd like to come back to this q to the 2/3. I want to look at that. Because we argued that if you hadn't reduced, it could have been written as q to the what? 4/6, right? That brings up an interesting little point here. Because if I translate these two to square, or I better be careful, I started to say square roots. Bad move. This is going to be a cube root, right? I want a radical. So this is the same as what? You tell me what to write here. What's my index? The 3. And this is q to the 2nd. Or, what could I do? I could have written q and done that. That's not quite as obvious. But note, these, in essence, are the same. Right? Taking the 6th root of q to the 4th is how you would interpret this. Okay? So let's say I give you, I'm creating a problem here maliciously. Now your first reaction is I can't do anything, correct? Now this is the same as my q to the 2/3. This is, no, hold it, no, this is the same. Here's my q to the 2/3, here's b to the 2/3. So we said this was the same as the 6th root of b to the 4th. Okay. Help me out. What goes inside? A to the what? I've got an a to the 9th, an a to the 12th. Any other votes?
9. It's 9.
3 9s? Okay, let's look at this. This was a to the what? 3/2. That's understood. So I have a to the 3/2. So I want to have something with the 6 down here rather than a 2. So I multiply here by 3 and here by 3. So I'd have a to the 9th over 6, 9/6. So this is a to the 9th. But now what can you do because they're both the 6th roots? The same index. So what can I do as my next step? The root times the root is the root of the product of what's inside. So I could argue that this then is the 6th root of a to the 9th, b to the 4th, where here I could not multiply because they did not have the same index. So I can change a problem. What couldn't be combined can now be combined because I get what? The same index. that is something noting, or worth noting, looking ahead. Okay, Pam, question.
Okay, so if that was a problem, would you simplify it further, or would you leave it as that as the answer?
Well, if I was given something like this, that's about all I could do. Now, if I'm going to work with fractional exponents, that's a different issue. I could translate this one immediately into what? A to the?
Well, I was thinking more of, you have a to the...
I think I'm going to get to your
Okay,
question.
go ahead.
What would you have here in this first factor? Writing it with fractional exponents. A to the what?
3/2.
3/2.
3/2. Do we see that? That the square root of a to the third is a to the 3/2. Okay, this is b to the 2/3. Now, with fractional exponents, we try to do what? Keep the fraction as a what? Reduced fraction. Okay, now I'm looking here and realize that this is a to the 9th 6 roots, so that's really a to the 9 6. So if I look at this again, it's a to the 9th, b to the 4th, to the 1/6, then I realize that that's 9 over 6, which is my 3/2, 4 over 6, which is my 2/3, which brings me right back to there. So if I see something with common factors, that is the 9 over 6 I can reduce, the 4 over 6 I can reduce, oftentimes I will go to this and then slide back to here. But the point is, you can change the appearance of a radical, getting the same index, and at times this is an important thing to be able to do.
Okay, that wasn't really my question. I mean, it was close. I know we had taken, if we had a to the 9th, wouldn't that be a to the 3rd times a to the 6th, and you'd end up taking a out? So you'd want to leave it like that.
Simplifying.
Simplifying
Okay.
it, right.
So what you're saying, you could have seen this as the 6th root of a to the 6th, a to the 3rd, good point, times the 6th root of b to the 4th. Yes, you could. I see where you're headed. Yes.
Okay, but so for if we were given that as a question on the test, would we leave
Well,
it
that's
as
a
the
reasonable answer, that you would have a to the 6th root of a cubed, but then what would you be inclined, oh, Curly, you screwed that up. That is supposed to be the 6th root of b to the 4th. That's improved, but what do you still have?
Well, you still have
A common factor here that you could deal with. All I was trying to get at is the form can be quite different. Now, where I was headed
Okay.
was, let's say I have, okay, can I do this? If I had a square root added to a cube root, so let's say I have the square root of a to the 9th, no, a to the 3rd, added to the 6th, wait a minute, cubed root of b to the 2nd. It doesn't look like I could do anything there. And what I think I might be inclined now is to do something like this and say, that's a to the 2nd. So the question, as I look at this, if the radicals aren't the same index, there's no hope at all in doing what? Adding them together. But if I say, well, wait a minute, that's the 6th root of a to the 9th plus the 6th root of a to the 4th, then there is a possibility, if I had some other terms, that suddenly I'm dealing with 6th roots of the same thing and maybe be able to add them. Here I can't, but at least I have them in what form? The same index. It's just your ability to play with radicals going back and forth to fractional exponents. This ability, I'll slide over here just for a minute, Debbie. This ability to rewrite radicals with indexes differently and translate them to fractional exponents is what tends to make this a little bit difficult. It's not with the problems we've been doing earlier in the set. Now I'm going to come back to the book. I don't know if I have that set up. Let's see what's there. I need to get down to the next part of the text because you'll note the directions here. It says by first writing it in what? Exponential form. So let's come off there for a moment and see what we want to do. simplify the radicals. And so the text is trying to get at that. If I look at 58 and 62, this is the same game. Because what do I have? An 8th root of m to the 4th. So what do you note? The index and the exponent on the variable are what? They have a common factor. So this is what I was trying to get at. And again, this is a problem that's at the end of the set suggesting what? And the comment is, it's hard because it's at the end of the set. Well, it's also anticipating what? Intermediate level content. So there's the obvious here. Can I simplify this? And what you may not see here becomes much more obvious if you realize this is m to the 4th to the what? The 1/8, and you immediately see that the 4 over 8 reduces to what? 1/2. This is m to the 1/2. And so what are you supposed to do? Translate this back now to a what?
A radical?
A radical, which is the second root of m to the 1st. Now let's compare these two. What have I in essence done? I've divided the index and this exponent both by what? 4. Okay, the index was 8. This exponent was 4. It was like having 4 over 8. So I could have written this as m to the 4 over 8, which became m to the 1/2. So the question is, do you have to go from here through all this, or can you just see that as a simplification? That's the kind of thing that the text is pushing. Well, let's do one more. Okay, back to the 58, same idea, number 58. We have what? The 9th root. And is that 27 to the 3rd?
Yes.
Am I reading that right? Okay. Oh, I like that because I see something else. What's 27?
3 cubed.
3 to the 3rd. So I have 3 to the 3rd to the 3rd, which is 3 to the 9th. And 3 to the 9th to the 1/9 is 3. Okay?
Did you get that?
Okay, this is 3 to the 3rd to the 3rd, so that's 3 to the 9th. And this is a 9 in the index. So we know that that is going to be 3 to the 3rd to the 3rd to the 1/9. 3 times 3 is 9, times 1/9 is 1, and so that is going to be a 3.
That's the answer?
I don't know if that's supposed to be the answer, but anyway, let's go ahead. The way this was set up, we have 27 to the 3rd to the what? The 1/9. Otherwise, it was not necessary for you to see the 27 as 3 to the 3rd. That was just fun. Okay, the 3 over 9 becomes 1/3. So this is 27 to the 1/3. So in terms of a radical, that says what? I'm taking the cube root of 27, but that is 3. So I don't know what they did at the end because we don't have the answer.
But,
Yes?
nope, never mind.
This might be all that the text intended, but I'd certainly feel badly if I didn't see 3. Okay, Debbie, we've had as much fun as we can really afford this morning. We started with Rod Stewart, right?
Correct.
And what did you decide to close to?
Rod Stewart, I know I'm losing you.
You're not kind this morning. I know. Oh, homework assignment before we go to that. Thank you. I'm going to have to come back to the book. After all this fun we've had, it would seem a shame not to do 1 through 62. Oh, wait a minute. There's some neat stuff up through 76, of course, without the green. So 1 to 75 odd. And we covered those, I think, adequately. Are those calculator problems in that? Okay, scratch that. 1 through 61 odd, sorry. 1 through 61 odd. And now to Rod Stewart. Have a great morning.